Hello everyone and welcome back. This is part 3 of Datum system videos and the last part for this series. So let's get right to it. Let's see. So we have here Datum system part 3 and we will talk about the common reference. So we do have a definition for this. Associated elements that constructs the common reference are constrained by orientation and location one from another. Okay, so we have here some marking examples. Marking use of a double letter separated by a line. This one is the most used one. And here is how it looks like, right here. Okay, adding complementary indicators NX, N representing the surface number used to collect. It is placed in the right side of the datum attached to a surface, and this is how it looks like. So this indicates the datum B should be made from 6 surfaces, okay? Another example is when it is placed above the tolerance frame that indicates the datum, like this. Okay, so the datum is also asked by the drawing to be evaluated. I don't know, it could be anything here. And it asks by the drawing to be evaluated 6 times. So datum B will be a common reference zone from 6 surfaces. Datum placed on the tolerance frame that use more lines that indicates all involved surfaces. I haven't seen this one in a long time, but it is out there. So it's just like this one, but with this one it indicates specifically the zone, each individual zone with an arrow. Okay. If not all characteristics that construct the datum are necessary, the datum frame will have a complementary indicator in the reference frame, PL, SL, PT, and the orientation symbol. With the exception of the case when the surface is evident. Okay, let's see what this means. Okay, so when you see in a tolerance frame, for example, datum B, PL. What this means that it's the indicator, the complementary indicator when only the plane is necessary. So B is only the plane is necessary. Okay. When we have SL is when only a line is necessary from datum B, and when we have PT is when only a point is necessary from datum B. When you see the orientation symbol like here, like we see here, is when the datum is constrained by rotational degrees of freedom only, not its location. So the location is not important, only the rotation from the datum is important. Move on. We have a common datum or datum system taken from a cylinder and a plane according to ISO 5459. In the first example, right here, okay, the cylinder is considered the primary datum and the plane is the secondary datum with orientation constraints. If the cylinder is inclined, then the plane has to follow. This is what it means, okay? If the cylinder has an inclination, the plane has to follow the inclination, so it has to be perpendicular, the plane has to be perpendicular on the cylinder. Okay, example number 2, right here. The plane is the primary datum and the cylinder is the secondary datum with orientation constraints. If the plane is inclined, the cylinder has to follow. Now it's the other way around. If the plane has an inclination, the cylinder has to be perpendicular on the plane. Okay, and then example number 3. The plane and cylinder construct a common datum. The orientation and location of the elements are constrained from one another. The intersection point between the axis and the plane is the common datum. Okay. For our first example, the cylinder and the plane, in order to construct a common datum, we will go and make a cylinder first. Okay, so we are still working with nominal values because we don't have a mesh. This is just the CAD model that I constructed. Okay, now let's bring the measuring principle and copy as actual element. Okay, and now let's rename this as datum A. I hope okay for this one as well. Good. And now let's make the plane as datum B. Autoplane nominal and construct datum B. Wait and close. Again, copy as actual. So now that we have the plane and the cylinder as separate datums, right? We have to construct also the common datum between them. So as we said in the presentation, the common datum will be the intersection point. So we will intersect the datum A with datum B, and this will be A minus B. Wait and close. Again, copy as actual element, and there you have it. Other examples of common datums. So another example of common datums is this one formed from 5 cylinders, as we see here. Okay, so 1 is the real surfaces of the cylinder, 2 is the simultaneous associated cylinder, 5 cylinders with variable diameters constrained by orientation, so they have to be parallel one from another, and location, theoretical exact distance d, the diameter from all of them, and theoretical exact angle of 72 degrees between them. Okay, and 3 is the common reference median line formed from the 5 cylinders, so the median line from the 5 cylinders, and plane that contains the median line and the axis from a cylinder. Okay, so this is a plane, imaginary plane. It's just an imaginary plane that cuts through the middle, the center axis, and for example this cylinder and its axis. So this is the center and this is the plane, right? Okay, this is the center axis, and this is the plane that goes through the center axis, and the axis of the cylinder. Okay, so think about it like this: you go from here to here to here to here to here, just like this. But this is just to show you exactly what's going on behind. For our second example, where we have the group of the 5 cylinders as the common axis, as the common datum, we will have to construct exactly as the drawing asks, a fitting cylinder between all of them. Okay, so let's select all of them, and as we see, the fitting cylinder goes through the center of each cylinder from here, and that means that it it respects the drawing because it has the diameter from the cylinders, and it goes through all of the 5 axes of the cylinder, resulting in a common axis from those 5 cylinders. Good. Let's put again the measuring principle as actual element, and we can also rename common datum A. Just a second. So this is datum A, made from all of them. Okay. Second example, we have the two parallel cylinders. Okay, so long story short, just to notice, we have a distance, a theoretical exact distance from datum A to datum B, and when we have a common reference A minus B, it's the median line formed from those 2 cylinders. Okay, so this will be, in this case, the common reference, common datum. Third example, the 2 cylinders and the common datum between them. So how do we do that? First, we have to define the cylinders. Okay, let's define them. We have one here, create, and another one here, create. Okay, and let's rename them. This one will be cylinder A, datum A, for example, and this one will be datum B. Okay, now we have to put the measuring principle as actual elements as well for both of them. And now we have to construct a symmetry line between the datum A and datum B. This will be our common reference, datum A minus B, or AB, sounds better. Again, copy as actual element, and there you have it. You have the common reference between A and B, and let's see them. Okay, like this, then rotate it. Let's rotate it like this. Okay, and let's clip the plane in the middle to see the median line from the cylinders. And the last example, the most used common datum, the axes of the cylinder are combined to form a common datum, exactly as we talked earlier. This is the most used one, and probably where all of you are used to see this common datum. Okay, and for our last example, we have the common reference from 2 cylinders. Okay, let's see how we should do this. So first we define the cylinders. Okay, and this one as well. Okay, close. Let's rename them. Say datum A, datum B again. Okay, select them both, Set the measuring principle copy as actual elements. Remember, this is only available when you don't have a mesh model. If you would have a mesh model, you will have to make reference construction. Okay, so you probably have here reference construction, or if not, fitting element. Okay, so reference construction, I think we have reference construction only. Yeah, no, we don't have it. Okay, so let's move on. Again, copy as actual elements, and now in order to take the whole axis of the cylinders, we will have to make also planes. So we make this plane from here, plane 1, create and close, and we will make also this plane from here, plane 2, create and close. Select the planes, measuring principle copy as actual element, and now we have to construct the intersection points. Okay, so we will do it like this. Point 1 between datum A and plane 1, create, oh, not create and close, just create, but we will do it again. Point 2, datum B to plane 2, create and close now, and set again the measuring principle for both of them as actual elements. And now from these two intersection points we construct a line, 2-point line. We select the points, point 1 and point 2, and there we have datum A minus B, the common datum. Create and close. All the surface is taken, so all the axes from the cylinders are taken, and you constructed datum A minus B, the common datum. Let's talk about datum targets. So there are very little reference elements with large dimensions that assemble with their counterparts with the whole length and the whole width. Okay, most of the times the assembly interface is limited to one or more points, lines or small zones. Furthermore, non-planar surfaces or patchy surfaces made by forging, injection, casting, welded parts or parts that are subjected to bending and deformations are assembled using the whole surface on rare occasions because it could lead to results with errors. The evident solution is to use only the points, lines or zones from the part that are pertinent to use, called datum targets. Okay, so we have here some examples of datum targets. We have the example of a point. So this is a datum target of a point. This is a datum target of a line. This is a datum target of a surface. And we have here some more examples where surfaces can be used. So indirect surface indicator, surface has to be within 30 by 20 millimeters, noted like this on the drawing. Direct surface indicator, surface has to be within 30 to 20 millimeters, nominal data highlighted. Square surfaces, so we have a square that has to be within 5 millimeters square, okay. And diametral surface, we have a diametral surface of 5 millimeters in diameter. Target datums on a plane that construct a datum, nominal data specified on the location of the target datums. Okay, so these are the target datums. We notice that it has to be a target datum of 4 millimeters in diameter surface, and we have the nominal data specified from the margins of the part. So we have 7 millimeters here, 6 millimeters here for this one, and so on. And we see here that datum A is constructed from A1, A2 and A3. Okay, the next one is target datums on a circle or cylinder that constructs a datum, nominal data specified as angular theoretical data. Okay, so again we have A1, A2 and A3 forms datum A, and we have angular theoretical data for all of them. Okay, and the last one, this is a little tricky because you will not encounter this on all of the drawings, just on some of them, and I personally never encountered them. I never worked with motion movable datum targets like we have here, but the motion of the movable datum target, which is given by the direction of the movable modifier, is perpendicular to a line going through the datum targets A1 and A2. So we have here datum targets A1 and A2, and the motion, the arrows like here, indicates where the datum targets can move, right? So it's perpendicular to the line formed from A1 and A2. It's perpendicular to this. Okay, so imagine it's perpendicular. It can only move like this on this surface, and for this one as well. Okay, and the motion of the movable datum target, which is given by the direction of the modifier, is parallel to a line going through datum targets A1 and A2. This one is parallel to the line. It is parallel, which means that it can move only parallel, only like this. Okay, and this one can move like this. This one can move like this. Okay, the movable datum targets tells us that we can move the point, line or surface to include some deviations on that area in the direction that the movable datum target is facing. So deviations are allowed on that area of the movable datum target. Thank you for watching. Leave a like if you liked what you saw. Subscribe if you like this type of content, and until next time, have a nice one.